Hi friends, I am Manibhushan. I am going to discuss today univariate time series model, and this is the today I am going to talk about like a auto regressive model. You can say the AR model. This is the very important model to use in a forecastings. So I think it is helpful for everyone if you are doing the any advanced research. So let's the AR model is the most basic building blocks of a univariate time series, and we have seen before univariate time series are a family model that use only information about the past of the target variable to forecast its future. So they do not rely on the other explanatory variable. So univariate time series model, it can be like intuitively understood as a building blocks, you can say, like, and they added up from simplest model to complex model, and that combined the different effects described by individual model. So the AR model is the simplest model of the univariate time series model. So let's try. And in the future, just we will see here the like we will build up from a AR model to the SARIMA models. So don't confuse. And after some time we will see the MA model. And whenever if we combine like the AR and MA, so AR, MA, RIMA models also you can see. So with the AR modeling, the simplest building blocks, and we would do the unrealistic to expect a great predictive performance on most real life data sets. So although let we could have see the some basic example. So AR model is a great start learning about the univariate time series. So let's see the auto-regressive model. And auto correlations is the past influence the present. So I am collecting a data from Kaggle. So this is a process to import os.in where Kaggle underscore config underscore dir will equal to slash content slash drive slash my drive underscore Kaggle, and this is the like a driver's Kaggle's. So percentage cd and slash content driver my driver, this one is the as it is. And then I have taken like a API Kaggle datasets downloaded USGS earthquake datasets. And if it is like sometimes we will see like a zip files, so you can see here like the zip can be converted into the CSV files. This is the algorithms we can convert like a zip. And import panda as a PD, import numpy as a NP, and I am collecting a data like a database as CSV, and this is a, so you can see here environment methods. So I have collect this data, so earthquake database. So this is the earthquake database I have collected. So in this data you could see like I am going to the describe this data. So equation of describe, so there are the number of the rows and columns in this data. So you could see the like the earthquake, I have given a variables eq dot shape. So you can see the 23,412 rows and 21 columns. So you could see the columns like latitudes, longitudes, depth errors, depth, semantic stations, magnitude. So these are the number of columns. So you could see here all these columns. If you want to see the more the like a data informations, so all 21 columns has been given, like a data types is also mentions. So date, time, latitude, longitude, types, depth error, depth, seismic stations, magnitude type, magnitude error, magnitude seismic stations, azimuthals, gaps, horizontals, distance, horizontal error, root, mean, square, id, sources, location sources, magnitude sources, status. Okay, so all column has been given and we can see here. Let's see, but I want to see here, so how many null sets in these columns. So you can specify here like a number of the columns in this data. So yes, it contains like a depth error columns has a 18,951, depth, seismic stations. So we want to remove these columns. So removing columns with the most of null values, and after that we could see here like your shapes will be look like so your rows as it is same, so but it will change, like you have removed like 8 columns, 1 2 3 4 5 6 7 8. Okay, so you could see here 8 columns. So I hope it's clear why do we are removing these columns, because your data you are applying an algorithm. So if you want to see like your algorithms is working properly, so you need to remove all null sets. If the contains the more null sets, so you can remove all these columns. Now let's see, I want to see the type. So type means if you see in the like a column type, so you can say earthquake, but do you want to see is it has more types? So yes, you could see here like if I write here type dot value underscore counts, so you can see the earthquake, nuclear explosions and rock burst. These are the types. So there are 4 and most of the earthquakes types contains in this data, right? Similarly, you can also want to specify some equations like types, rock burst, explosions, nuclear explosions. Okay, so you can write here, and then you can also count here like 23,000. Look here, so now you can say 23,232. After that I am importing like a matplotlib, and I want to see here the longitudes and latitudes. So I can easily plot it's a longitude and latitudes. After that, if I want to see like a latitude longitudes with the plotly is the another library, so we can also see here your data. But our purpose is like we want to see some important things here. So first, autocorrelations means the past influence present. So let's see. So what is the auto correlation? So first you try to understand. So suppose imagine like somebody has gone like at the doctor's place, and they are considered the waiting line at a doctor's, and imagine that the doctors has a plan in which each patient has 20 minutes with them. So if every patient takes exactly 20 minutes, this work fine. But what if the patient takes a bit more time, and autocorrelations could be present? So if the durations of consultations has an impact on the durations of the next consultations, so if the doctor needs to speed up consultations because the previous consultations took too long, so you observe correlations between the past and present. Past value influence a future value. So in this data, just I want to see same thing here. So because I have already described this data, and I want to the some, if you I want to the some profile reports. So the pandas has a library, and it has uh, some profile reports is just some basic package. So if I want to see the some basic reports, so we could see here like overview, how many data sets, number of observations, and what are you. So you could see here, and then we can describe each and everything. So but we didn't need here. Now I am going to the earthquake data and date. So panda to date, to underscore date time, and date, so error and queries. And now I want to convert your data into date time, like a date time and UTC true, and now I am converted this data like years. So you can see here equation year and will equal to panda to date time equations date time. So you can do the other way also, don't worry. If you know the better algorithms, you can write there. So let's see now the filter the earthquakes with a magnitude of 7 and higher. So I can write the equation again, equations magnitude, it's greater and equal to the 7, and we could see here. So it's a basic output we could see here. Similarly the compute count the earthquake per year. So earthquake the per year, so we will write, I can write here eq dot group by years and dot count, and earthquake per year I want to see a earthquake per year I log like a first 2 minus 2 and 0. So make a plot the earthquake per year, and you can fix like a AX earthquake per year dot plot. So we could see, so in the 2010 it has been increased like the number of the earthquakes, and after that you could see here. Now the another just, so in this report so here we can see here this code should give us the graph display, and we can see that there might be some relationship between years, 1 year and it's the higher, and the 1 year it's the lower. So this could be due to the negative autocorrelations. Remember that negative correlations implies that the higher value in one variable corresponding to the lower value in the other value. So for the autocorrelations, this means that a higher value this year corresponding with a lower value next year. So this is the evaluations of the number of earthquakes per year we have already seen in this graph. And now you obtain the number of the earthquakes per year, so you should check auto correlations numerically. So we need to find out whether there is a correlation between the number of the earthquakes in any given year and the year before it. So you can use the same method computing like a correlations as seen, and correlations is computed pairwise in the two columns. So let's see, just we can applying here like the one variable shifts panda.data frames, and this year I have changed like a earthquake per year, and past year I have written like a earthquake underscore per year dot shifts, and just I can write so this year and past year, and just x will equal to shift dot plot and x dot set underscore y level number of earthquakes and PLTs that show. So just if I use, and we could see here like this year and past year shifted data, so this work well except for the one things. As you can see in the data, there are observations from 1996 to 2014, and this means that you don't have a value for a past year from 1996. So you could see here 2010 to 14. So this means that you don't have a value for the past of 1996. This introduce like a non-value, missing value. This type of broader effect is a very common time series analysis and the best solution. So let's see. Just now we are going to write here next the shift dot drop on. So this steps to the compute the like a Pearson correlation coefficient using the code, and we will see, we have already seen in the previous video. So the compute the correlation matrix shift and data frame shift out correlations, and we could see here like this year correlation is perfect correlations past and very low correlations between the this year and past year. You could see here, so very low correlation. So in this we can easily interpret this autocorrelations because it has a low correlation. So now the regularly the correlations autocorrelations can be a positive or a negative. So positive autocorrelations means that high value now will likely give the high value in the next period. This, and we observe like same procedure in like a stock trading, and the many people want to the buy stocks, its price goes up. So this positive trend makes a people want to buy these stocks, and even a more as it has a positive results, and more people buy stocks and more it goes up, and more people may want to buy it. So try to understand the positive correlations. So the positive correlations also work on a downtrends. So it's today like a stock value is a low, and then it is a likely that tomorrow value would be even lower. So as the people started selling, so when the low of the people sell, the value drops, and even more people will want to sell. So this is also a case of positive autocorrelations as the past and present go in the same direction. So if the past is low and present is low, and if the past is high and present is high. Now the similarly we try to understand like negative autocorrelations exist if two trends are opposite. In this case, doctors consolidations just we have already discussed in the previous example, durations example. So if the one consultation takes the longer and next one will take shorter. So if the one consultation takes the less time and the doctor may take a bit more time on the next one. So if you have applied the code, you have observed a correlations of around 0.31 between current year and past year. This correlation is a positive rather than negative as was expected based on the graph. And this correlation is a medium strength. It seems that a correlations that capture the trend in the data. So same you can see here like my next. So first we want to see here like the trend in this number, the earthquake is a bit higher in the earliest year, then a bit lower in the certain period, and in the last year so the bit higher again. So this is the problem as the trend is not a relationship that you want to capture here. So let's see first stationarity. So like the problem having a trend you data is a general in a univariate time series modeling. So the stationarity of the time series means time series does not have a trend. So it is stable around the same average. If not, you say the time series is non-stationary. So AR model can theoretically have a trend coefficient in the model. So stationary is an important concept in the general theory of time series. So it is a better to learn how to deal with it right away. Lot of models can only work on the stationary time series. A time series that is strongly growing or diminishing over time is obvious to spot. So but sometimes it is difficult to tell whether a time series is stationary. But this is the whether the we will apply here ADF like a augmented Dickey-Fuller test, common in useful. So the augmented Dickey-Fuller test is the hypothesis test that allows you to test whether the time series is stationary and not. So we could see here from stats model .tsa.stats tools import ADF Fuller and result AD Fuller earthquakes per year Dropana print result and p-value results 1, and if the p-value less than 5% print stationary and else not stationary. So we could see here like our data look like this. We have printed all these value 1% minus 3, 5% minus 2, 10% minus 2. Okay, so we could get here stationary. So now we have gotten in this case the data like you will see the p-value of the smaller than 5% reference, and this means the series theoretically stationary. We don't have to change anything to apply the AR model. So there is no need to change anything. After that we try the differencing a time series. So even through the ADF test tells you that data is stationary, you have seen that the autocorrelation is positive. So where you would expect a negative one. So the hypothesis was that this could be caused by a trend. So you now have the two opposing indicators. One tells you that the data is stationary and the other one tells you that there is a trend. So to be safe, it is better to remove the trend anyway. This can be done differentiation. So there are two ways and it depends on. So let's see the differentiation. So differentiation means difference data earthquake per year dot differ the dropana and plot the differentiation data and differentiate the data dot plot ax dot set y order level and differentiate this number. So you could see here your data like this. So whenever you have plotted, you could see here differentiation means the rather than a modeling an original value of the time series. So you model the differentiation between the each value and the next. So let's see, there will be probably not a trend in differentiation in this data. So now see the whether this has switched your autocorrelations to the right direction. So you can compute the correlation coefficient as you did before. So let's see and write the sum code like a shift, just I have done already in the previous data. PD data frame and this year differentiation, past year differentiation, shift underscore the plots and different numbers of earthquakes. So let's see in the, so if you see the differentiations and you could see like a previous data. So here let's see, both are look like a same. So the correlations and coefficients. So if you see here, so autocorrelations and differentiation data, and now you obtain the correlations coefficient is the minus 0.30. I think you have gotten minus 0. So here is negative minus 0.37. So we can see have the successfully removed the trend from the data. So your correlations is now the negative correlations, so that you expected if there are more earthquake 1 year, then you generally have a fewer earthquake the next year. Now so after that let's see the autocorrelations and the differentiation this data. So lag in autocorrelations. So beside the directions of the autocorrelations, the notions of lag is important. So this notions is applicable only the autocorrelations and not in a regular correlations. So the number of lags of an autocorrelations means number of steps back in time that have an impact on the present value. So many cases we will see if the autocorrelations is present, it is not just the previous time steps that has an impact, but it can be many time steps. So applied to a doctor's consultations durations example, just we have already discussed. So you could imagine that doctor have a very long delay in one consultations and that they need to spend up for the next 3 consultations. So this means that The third speedy consultations is still impacted by the delay one. So the lag of autocorrelations would be at least 3 steps back in time. 3 steps back in time. So doctor consultations durations example is a very intuitive, and it is a very logical that the doctor had a limited amount of time. So in the example the earthquakes per year, there is not such a clear logic that explain a relationship between the past value and the current value. This made it difficult to intuitively identify the number of lags that should be included. Great tool to investigate autocorrelations in a multiple lags at the same time is to use autocorrelations plot from the states model package. So, and this code like ACF autocorrelations functions autocorrelations as a functions of lag. So note that our choice like a 20 lags is arbitrary. It for the plotting the purpose only. 20 lakhs means the 20-year back in time. So this should be enough to show relevant autocorrelations, but the 40 even the more would be the acceptable options too. So let's see. Here stats.graphics time series plot, import PL2 ACF, import matplotlib pyplot as a PLT, and plot ACF differenced underscore data lag 20 and PLT show. So we are talking about 20-year back. So let's see the autocorrelations. So we will obtain this and this figure. This plot shows which the autocorrelations are important to retain. On the y-axis, you see the correlations coefficient between the non-lag data, original data, and the lag data. So the correlation coefficient is between like -1 and 1. On the x-axis, you see the number of lags applied. In this case, from 0 to 20. So first correlation is 1, as this is the data with the 0 lag, the original data. Similarly, let's see the partial autocorrelations. So you should look like autocorrelations value and that are the least higher than 0.2, and if you see in the lower, we have seen in the previous data like a -0.2, so anything below they can be the considered the noise. Using 0.3 or 0.4 as a minimum value is also possible. So there is no strict guidelines to interpret in the correlations coefficient, as in some domain data are noisy by nature. For example, in social studies, when working with measurements from a questionnaire studies, and you will often see much more noise than when working with the like a precise physics measurements also. So you can see here the blue colors. So the blue area in the graphs allow you to detect visually which autocorrelations are just noise. If the spikes goes outside the blue area, there is a significant autocorrelations, but if the spikes stay within the blue area, the observed autocorrelations is insignificant. So you can generally expect the autocorrelations to the higher lag that are closer to the present and diminished towards further away moment. So we observe the first spike, which is a very long, and this is a normal, and it is the original data. So the correlations between the variables and itself is always 1, means 100%, and the second spikes is the correlations with the lag 1. This is the autocorrelations that you have computed before using the correlation matrix. So the correlations coefficient is minus 0.37, and you see this again in this graph. So the remaining autocorrelations are the less strong. This means that to know the number of the earthquakes today, we should mainly look at the value of one lag back in the current example. So this means the number of earthquakes last year, there were many earthquakes last year, and we can expect a fewer earthquakes this year. This is indicated by negative autocorrelations lag. So for the sake of understanding how excuse me, to interpret the further lags, imagine a different hypothetical like a ACF plot of only one positive spike at lag 5 and the other lags being all 0. This would mean that to understand this year's numbers of earthquakes, and you need to look what happened 5 years ago. If there were many earthquakes 5 years ago, so there will be the many earthquakes this year. So what happened in a between is not relevant. So since there is no autocorrelations with the previous 4 years, so the number of the earthquakes in the previous 4 years will not help you determine the number of earthquakes this year. Similarly, just if we are using like partial correlations, so the partial autocorrelations is the another plot, and you can see in this figure the difference between the autocorrelations and partial autocorrelations is that a practical autocorrelations makes like a sure in the any correlations is not counted the multiple times for multiple lags. So the partial autocorrelation in the such a lag is additional autocorrelations in its inferior lag. So mostly mathematically you can say PAC like a yi and yi plus h, y minus I minus h. So you can get the covariance of the, you will start the data like yi minus h and divided by yi minus 1 till y minus h, and it will divide by the variance yi by yi minus 1. Similarly yi minus h plus 1 divided by the another variable variance like a yi minus h and 4 divided by the yi minus 1, and this way. So this is the theoretical way. But if I plot here the autocorrelations in this data with the algorithms, we could see like a partial autocorrelations, and the blue background is turning the graph PAC and the second lag outside the shaded regions, and this means that it would be interesting and to also include the second lag. So there is a one more questions has been arising. So how many lags to include? So now the big questions in the time series analysis is always how many lags to include. So this is called the order of the time series. So the notation, like if you write the AR1 means for order 1, ARP means order P. So order is up to you to decide. Theoretically speaking, you can base your order on the PACF graph, partial autocorrelations. So the theoretically tell you just take the number of the lags before obtaining the autocorrelations of 0 and all the other lags should be 0. You can also like a grid graph where the first spikes is the very high and the rest is the equal to 0. In those cases the choice is the easy. You are working with a very pure example like AR1. Another common case is when autocorrelations start high and slowly diminish to 0. In this case you should use all the lags where the PACF is not at 0. So you do the practice. So in the earthquake examples, there is still a bit of the partial autocorrelations on the further lags and it goes until a very far lags. Even you can spike like a PACF of the lag 18 here. 18, this could be means many things and may be there really is autocorrelations with the lags far away, or maybe hidden process is underlying that the AR model is not capturing well. So in a practice, you will try to select the number of lags that gives you model the best predictive performance. So the best predictive performance is often not defined by looking at autocorrelation graphs. Those graphs give you theoretical estimate. So let's see here now. If I define like a AR model, so some formula like AR models like a xt will equal to sigma I will equal to 1 to p and eta I x t t minus I and plus eta t means like a error term. So in this formula you could see here, so the AR model like you have defined form like you can't use the long, it as a long, we don't have the value to the plug into the formula. So the next step is to fit the model. So we need to find the optimal value for the each coefficient to be able to the use. So this is also the estimating the coefficient. So once you have a value for a parameters, it is the relatively easy to use the model. Just plug in the lag value and any machine learning theory. So the difficult part is always in estimate this model. So in the formula you see that the past value like xt minus I are multiplied by coefficient of eta. Yeah, you can say the phi I, the sum of this gives you like a current value xt. So AR model, so the different method we have been found to estimate the coefficient. One of the mode is the Euler-Walker methods. So UW methods, and now I am going to apply here from the stats.regressions.linear underscore model import a Euler-Walker and coefficient like a sigma Euler underscore Walker difference underscore data order will equal to 3 and print the coefficient minus coefficients and print a sigma and sigma. So let's see. So if the returns like a 1 in the delta functions, so let's see what happens. Just yeah, so just we have plotted like a coefficient like this 0.51, 0.34, 0.08, and sigma is 3.99. So the coefficient that you obtain with this we obtained with these are the coefficient for the each of the lag variables. So in this case the order 3, so that will needed to be applied for the 3 least value to compute the new value. So we can make a forecast by computing for the next steps based on the current coefficient. So the code for this we can see and try to get here like another estimate Walker AR coefficient with the order way, and we could see it is similar, so don't look there. So we need to go the next here. Yeah, right. Make the forecast and AR coefficients. And you could see here like this. So these are the algorithms. So we will see the obtain this plot, means the first value are the actual data and the last 10 steps. You could see here the last 10 steps. It might be like a 20 you can take according to your. It's a very interesting. So you can the last 10 steps are the forecasting data. So unfortunately you can see that the model has not captured anything interesting. So it is just a flat line. So but you haven't finished it. So let's try with and the order 20 this time and see whether anything improved. So let's see here. Let's try to the order 20 and I am going to the right here the coefficient sigma will work actually same algorithm look here, but I have changed the order 20 and you could see here just. So could you see the something like it's not a straight line, so you could see the something but it is correct. So the forecasting with the order 20 has the captured the something, so but it is correct. So is it correct and not correct? So we need to go the train test evaluations and training. So in this case let's apply the train test split and we will see the cutoff the last 10-year data sets and use them the test sets. And now we allow to fit the models using the rest of the data like a train test, and once we have fitted on the train sets we can compute the error between the test sets and your predictions. So let's see. Now the train test evaluations, just I have taken from the scalar.matrices import r square underscore scores train like list the differences the data -10 and test the test earthquakes like per year -10 and coefficient of the sigma will Walker's train order 3 and the value list train coefficients value list reverse. We have taken like a define the number of the years to predict like a 10 and we are using like a for loops and these. So just we have forecasted here, and we could see something. So this is a way we can easily, this is the way we can see the evaluations of the plot models with the order 3. So let's see. So you try and this model will work and you can understand to how. And next class I will discuss like other models like ARIMA models and something. So I hope it will be helpful for someone. Thank you very much.